Voltage, current, and resistance are fundamental concepts in understanding electricity. Voltage, also known as electromotive force, is the electrical potential difference between 2 points in a circuit. It is the driving force that pushes electrons through a conductor. Voltage is measured in volts. Think of voltage as the pressure in a water pipe. The higher the pressure, the more water flows. Similarly, the higher the voltage, the more electrons flow through a circuit. Current is the flow of electric charge through a conductor. It is the rate at which electrons pass a given point in a circuit. Current is measured in amps. In our water pipe analogy, current is the amount of water flowing through the pipe. The more electrons flowing, the higher the current. Resistance is the opposition to the flow of electric current in a circuit. It is a property of a material that hinders the movement of electrons. Resistance is measured in ohms. In the water pipe analogy, resistance is like a constriction in a pipe that restricts the flow of water. The higher the resistance, the lower the current for a given voltage. These three concepts are related by Ohm's law, which states that voltage equals current times resistance, or volts equals amps times ohms. This law is a cornerstone of electrical circuit analysis. If you know any two of these values, you can calculate the third. For example, if you have a 12 volts battery and a 6 ohms resistor, the current flowing through the resistor would be 2 amps, calculated as 12 volts divided by 6 ohms. Understanding the difference between these concepts is essential. A common mistake is to confuse voltage and current. Voltage is the potential difference, while current is the flow of charge. Resistance impedes that flow. These concepts are all interconnected and influence each other in a circuit. Voltage is the cause, and current is the effect, with resistance modulating the current's magnitude. Now let's discuss some practical examples. Consider a simple circuit with a battery, a resistor, and connecting wires. The battery provides the voltage, which pushes electrons through the wires and the resistor. The resistor limits the amount of current flowing in the circuit. The higher the resistance, the lower the current. If you were to increase the voltage of the battery, the current would also increase, assuming the resistance remains constant. Conversely, if you were to increase the resistance, the current would decrease, assuming the voltage remains constant. Understanding these relationships allows to analyze and design electrical circuits effectively. Another important concept is power, which is the rate at which electrical energy is transferred in a circuit. Power is calculated as voltage times current, or power in watts equals volts times amps. Power is a measure of how much work the electrical energy is doing. A higher power rating means that the circuit is transferring more energy per unit time. For example, a 100 watts light bulb consumes more electrical energy than a 60 watts light bulb. The 100 watts bulb converts more electrical energy into light and heat. The concept of electrical safety is critical. High voltages and currents can be dangerous and can cause electric shock or even death. It is essential to follow safety precautions when working with electricity. Always turn off the power before working on any electrical circuit. Use insulated tools and wear appropriate safety gear. Never work on electrical circuits in wet or damp conditions. Understanding the dangers of electricity and following safety procedures is crucial to prevent accidents. Electrical circuits can be classified into two main types: series circuits and parallel circuits. In a series circuit, components are connected end to end, so the same current flows through each component. The total resistance in a series circuit is the sum of the individual resistances. In a parallel circuit, components are connected side by side, so the voltage across each component is the same. The total resistance in a parallel circuit is less than the smallest individual resistance. Understanding the behavior of series and parallel circuits is important for designing and troubleshooting electrical systems. The concepts of voltage, current, and resistance apply not only to simple circuits but also to more complex electronic devices. Electronic devices such as computers, smartphones, and televisions contain intricate circuits with numerous components. These components include resistors, capacitors, inductors, and transistors, which work together to perform specific functions. Understanding the fundamentals of electricity is essential for comprehending how these electronic devices operate. To measure voltage, current, and resistance, use a multimeter. A multimeter is a versatile instrument that can measure various electrical parameters. When measuring voltage, connect the multimeter in parallel with the circuit component you want to measure. When measuring current, connect the multimeter in series with the circuit component you want to measure. When measuring resistance, disconnect the circuit from the power source and connect the multimeter across the resistor. Ensure that you select the appropriate range on the multimeter to obtain accurate readings. When working with electricity, grounding is important. Grounding provides a safe path for current to flow in the event of a fault. Grounding helps to prevent electric shock and damage to equipment. Grounding systems typically consist of a grounding electrode, such as a ground rod, connected to the electrical system. The grounding electrode provides a low resistance path to earth, which helps to dissipate fault current safely. The National Electrical Code, or NEC, provides guidelines for grounding electrical systems. The NEC specifies the requirements for grounding electrodes, grounding conductors, and bonding. Bonding is the process of connecting metal parts of an electrical system together to create a low impedance path for fault currents. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electric shock. Electrical codes and standards provide requirements for the safe installation and operation of electrical systems. These codes and standards are developed by organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, or IEE. Adhering to electrical codes and standards is essential to ensure the safety of people and property. In addition to voltage, current, and resistance, other important electrical concepts include capacitance and inductance. Capacitance is the ability of a component to store electrical energy in an electric field. Capacitors are used in circuits to store energy, filter signals, and smooth voltage fluctuations. Inductance is the ability of a component to store energy in a magnetic field. Inductors are used in circuits to store energy, filter signals, and create oscillating circuits. Understanding capacitance and inductance is essential for designing and analyzing more complex electronic circuits. Alternating current, or AC, is a type of electrical current that periodically reverses direction. AC is used in most power distribution systems because it can be easily transformed to different voltage levels. Direct current, or DC, is a type of electrical current that flows in one direction only. DC is used in batteries, electronic devices, and some industrial applications. Understanding the difference between AC and DC is important for working with various electrical systems. Electrical transformers are devices that transfer electrical energy from one circuit to another through electromagnetic induction. Transformers are used to step up or step down voltage levels. Step-up transformers increase the voltage, while step-down transformers decrease the voltage. Transformers are essential components in power distribution systems and electronic devices. Electrical generators are devices that convert mechanical energy into electrical energy. Generators are used in power plants to generate electricity. Generators operate on the principle of electromagnetic induction. Mechanical energy is used to rotate a coil of wire in a magnetic field, which induces a voltage in the coil. Electrical motors are devices that convert electrical energy into mechanical energy. Motors are used in a wide variety of applications, such as appliances, vehicles, and industrial equipment. Motors operate on the principle of electromagnetism. An electric current is passed through a coil of wire in a magnetic field, which creates a force that causes the coil to rotate. Electronic components are the building blocks of electronic circuits. Common electronic components include resistors, capacitors, inductors, diodes, transistors, and integrated circuits. Understanding the characteristics and applications of these components is essential for designing and troubleshooting electronic circuits. Resistors are used to limit current flow in a circuit. Capacitors are used to store electrical energy. Inductors are used to store energy in a magnetic field. Diodes allow current to flow in one direction only. Transistors are used to amplify or switch electronic signals. Integrated circuits, also known as chips, contain millions or billions of transistors and other components on a single piece of silicon. Digital electronics deals with circuits that operate on discrete levels of voltage, typically representing binary values of 0 and 1. Digital circuits are used in computers, smartphones, and other digital devices. Analog electronics deals with circuits that operate on continuous ranges of voltage. Analog circuits are used in audio amplifiers, radio receivers, and other analog devices. Thevenin's theorem and Norton's theorem are powerful tools for simplifying complex electrical circuits. Thevenin's theorem states that any linear circuit can be replaced by an equivalent circuit consisting of a voltage source in series with a resistor. Norton's theorem states that any linear circuit can be replaced by an equivalent circuit consisting of a current source in parallel with a resistor. These theorems can be used to analyze circuits more easily and to determine the voltage and current at specific points in the circuit. Kirchhoff's current law, or KCL, states that the sum of the currents entering a node in a circuit must equal the sum of the currents leaving the node. Kirchhoff's voltage law, or KVL, states that the sum of the voltages around any closed loop in a circuit must equal 0. These laws are fundamental principles for analyzing electrical circuits and can be used to determine the voltage and current in various parts of the circuit. Electrical safety is always paramount. Follow all applicable electrical codes and standards. Always to energize circuits before working on them. Use insulated tools and equipment. Be aware of the potential hazards of electricity and take precautions to protect yourself. If you are not comfortable working with electricity, consult a qualified electrician. Electrical engineering is a broad field that encompasses many different areas, including power systems, electronics, control systems, and telecommunications. Electrical engineers design, develop, test, and supervise the manufacturing of electrical equipment. They work in a variety of industries, including power generation, electronics manufacturing, telecommunications, and aerospace. Electrical technology is a related field that focuses on the practical application of electrical principles. Electrical technicians install, maintain, and repair electrical equipment. They work in a variety of industries, including construction, manufacturing, and utilities. Understanding electrical concepts is essential for anyone working with electricity, whether it be an electrical engineer, an electrical technician, or homeowner. A solid foundation in electrical theory and practice is crucial for ensuring the safe and reliable operation of electrical systems.